Okay, so today we're going to do section 13.3 of the book, which is about infinite sets. Okay, now we're going to do actually two books, because in the handout, the packet that I gave you the first day of class, I have a chapter from my book called Infinite Puzzles. And there it's done much, much more clearer than in the book, easier than in the book. This book is made for high school students. Our book is made for college students, so it's easier. So what I recommend is that you first look at my book and then look at this Ross and Wright book. Okay? Okay. But we basically cover the same things. Okay. So we have to remember something. We were talking about functions. These are functions. Okay, so let's just do this. Is section 13.3, infinite sets. Okay, we were talking about functions, and there were special types of functions that we like called one-to-one functions. And then there were other special types of functions called onto functions. Okay, and then we had special functions that were both one-to-one and onto. Okay, and we call those one-to-one correspondences. Okay, they're one-to-one correspondences. There's other names for them, and I'd like to go through some other names. One is isomorphisms. Okay, which means if f from A to B is one-to-one and onto, it's an isomorphism. What it says is that A and B have the same size. They're the same size. These two sets, this is an isomorphism, and you say that A, set A, and B are isomorphic. Okay, that means that they have the same size. Let me give you an example. Okay, I have a set of fingers on my right hand. I have a set of fingers on my left hand. They are isomorphic. Okay, why? Because I can make a function from this set to this set such that it's one-to-one. No, two fingers go to one finger, and every finger here is hit. Okay, so these two sets, obviously they both have 5 elements, but these two sets are isomorphic because we can make a correspondence. There's another phrase that's used in my book. We say these two sets are equinumerous. Equinumerous. Numerous. Okay? Which means they have the same number. Okay? So let's just do some examples. Okay? The set of states in the United States. There are 50 states in the United States. There are also 50 governors in the United States. Okay? And basically every single governor can be matched up with a state. Every state can be matched up with a governor. So they're the same size. There's 50 of these, there's 50 of these, the same size. Okay? It does not work for senators. Okay? There are 2 senators for every state, and so it doesn't work for senators, but it does work for governors. Okay? The set of people in this country and the set of noses in this country. Okay? For every person, there's a nose. For every nose, there's a person. Okay? So these two sets are, this map is one-to-one and onto, and these two sets are isomorphic, that means the same size, or equinumerous, the same size. Great. Okay, so first I got to tell you a story. Okay, let me just say, this all totally makes sense and is totally understandable as long as we're talking about finite sets. But when we start talking about infinite sets, things get really strange. So I'm going to tell a story. The story is about Hilbert's hotel. So Hilbert was a mathematician who lived till the 30s, and he told over this story because he wanted to get the intuition of sets down pat. So here's the story. Hilbert has a hotel, And the hotel has, instead of 300 rooms, instead of 400 rooms, the hotel has an infinite number of rooms. Okay? And so the hotel has an infinite number of rooms. In other words, for every natural number, let's remember what a natural number is, for every natural number, 0, 1, 2, 3, 4, ... we're going on forever. For every natural number, there is a room. For every room, there's a natural number. Okay. So he has this hotel. Now, this is a make-believe hotel. There's no such thing as an infinite hotel. Just want to get the story straight. Okay. Now, what happens if one day Hilbert's hotel is full? He has an infinite number of customers. Then every single room is full. Okay? Along comes someone driving in a car, comes up to the infinite hotel, and he wants a room. Now, in every other hotel, let's say if there's a hotel with 300 rooms, if there are 300 rooms and there are 300 customers, then the room is full and there's a vacancy, no vacancy sign put up on the hotel. That's it. You just can't fill in. If there are 300 customers, you can't fill in 301 customers. So you just leave that alone. Okay? You say, I'm sorry, go down the road, find another hotel. But Hilbert said you can do something very interesting with Hilbert's hotel. Now, the idea is, what should you do with this new customer who just drove up in the car? What do you do with him? Okay? So one idea is, put him in room 35. There is no, if somebody's in room 35, you can't do that. What do you do with that customer? Okay? You can't put him in room 0 because room 0 is full also. You can't put him into the last room because there is no last room. Every single room is full. Okay? There is no last, what's the last number? There's no last number, there's no last room. Okay? But Hilbert has a solution. He says as follows. He says, get on your handy-dandy microphone in the hotel, and you tell everybody, look, it's 11:25. At 11:30, I want everybody to grab all their stuff, get out of their room, and move to the next room. So if you're in room 37, I want you to go and move to room 38. If you're in room 534, I want you to move to 536. 535. If you're in room 9,628, I want you to move to 9,629. If you're in room N, I want you to go to room N plus 1. Okay? Now, at 11:30, everyone's going to do this. They're going to scream, they're going to curse, they're going to be walking in their pajamas, they're angry, they're upset, etc., but they're going to do this. Now, after it's done, after everybody calms down, goes into their new room, guess what happens? There's one room available. What's the one room available? The 0 room. Okay? And you can take your new customer that was in the car and bring him in. Okay. Now, what just happened? So, that's an amazing thing. You've taken all your customers and you've moved them all one room over, and you've made one room available. That's an amazing thing. Okay? You cannot do that with a finite hotel. Because in a finite hotel, if you have 300 rooms, and you tell everybody to go to the next room, the guy in room number 300 doesn't have a place to go. He's stuck. Okay? You can't put him in room 0 because that doesn't help you. That just switched around everybody and made everyone unhappy. Okay, so what you just did was you have this set, the natural numbers, and there's another set called P for the positive numbers. Positive P is 1, 2, 3, 4, like that. Okay? And what you just did was you moved all your infinite number of customers into this infinite set. Okay? Now, so the guy in room number 0 went to room number 1. The guy in room number 1 went to room number 2. The guy in room number 2 went to room number 3, the guy, etc., etc. The guy in room number N went to room number N plus 1. Okay? So you've made this correspondence. Now, it turns out because you can make this function, these two sets, it's a one-to-one function, it's onto, these two sets are equinumerous, they're the same size. Now that's extremely counterintuitive, because if you look at it, this set has one less element than this set. The natural numbers has the 0, this doesn't. Okay? So what we're kind of saying, but I don't like this symbol, infinity plus 1, okay, here's an infinite set. Infinity plus 1 is the same size. We write the same size. We write the same size. We say A is the same size as B. We write it as this. Doesn't mean that they're the same size. Okay? It doesn't mean that, I'm sorry, it doesn't mean that they're the same sets. What it means is that the number of elements in A is equal to the number of elements in B. Okay? That's what that means. So when we say two sets are isomorphic, equinumerous, if the number of elements of A is equal to the number of elements of B. So what we just showed was the number of elements in the natural numbers is the same as the number of elements in P, in the positive numbers. Okay? Or infinity is equal to infinity plus 1. Okay? Okay. Another way of saying it is the natural numbers is equinumerous to the positive numbers. Okay? And again, that's a shocking thing, because I gotta say, the set containing 300 is not equal to the same size as the set containing 301 elements. So it doesn't work with finite sets. Mr. Hilbert didn't stop there. I'm sorry, he did stop there, but I have another story to tell about Hilbert's hotel. Okay? I don't know if Hilbert sold this hotel, the story or not, didn't. Okay? This is nice. Okay? So everybody's calm. He goes, he takes his new customer that was in the car, he puts him into room number 0. Everybody's happy, everybody's doing their thing. Along comes a bus. And since we're living in a very strange world which has infinite hotels, we also have a bus with an infinite number of passengers. And each one of the infinite number of passengers wants their own room. Okay? So this makes the problem infinitely harder. Okay? It's not, I need one more room. I need an infinite number of rooms. Okay? So what do you do? So here's a good way of solving this problem. Ready? You can't just put an infinite, you can't do this over and over. You can't just do this over and over and say, okay, everyone move to the next room, everyone move to the next room, everyone move to the next room. Because you have an infinite number of customers that you have to do that. It will take an infinite process to do that. Okay, so here's what you can do. You ready? You get on your handy-dandy microphone and you do the following. You say, everybody, it's 11:30. At 11:35, I want everybody to take all their stuff and go to the room that's twice the number of their room. Okay? So if you're in room 35, go to room 70. If you're in room 10, go to 20. If you're in the room 923, you go to 1846. Whatever x, whatever room you're in, n, go to 2n. Okay? Let's see what happens then. Okay? Let's see what happens then. Notice what happens. Which rooms will be full then? So everyone's going to do that. At 11:35, everyone's going to grab their stuff, really upset, etc., and they're going to do this. They're going to open their doors, look at their room number, calculate what double the room number is, and go to that room. At the end of that, which rooms will be filled? Which rooms will have people in it? Okay? Answer, the even number rooms. All the even number rooms will be filled. The odd number rooms, 2 times n is not going to be an odd number room. So everybody's going to go from all their rooms to the even number rooms. Then, what about your odd number rooms? All your odd number rooms are empty. They're finished. They're closed. Okay, so then what do? Okay, take your bus people, your infinite number of customers and your bus people, and put them into the odd number rooms. Okay, everybody's happy. You've just doubled their capacity. What I just showed was infinity plus infinity is equal to infinity. Okay? You had the infinite number of original customers plus the infinite number of new customers, and you put them into your infinite number of rooms. Okay? Let me show you another way of thinking about that. Okay? What you did was, you had your natural numbers. 0, 1, 2, 3, 4, dot, 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 dot. These rooms were all filled. Okay? And then you have another set called the evens. Okay? 0, 2, 4, 6, 8, dot, dot, dot. Okay? And you made a one-to-one correspondence between this set and this set. 0 goes to 0, 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8, n goes to 2n. Okay, n goes to 2n. And this scheme shows you how to make a correspondence between the natural numbers and the even numbers. This is exactly what you did with the hotel. You have all your rooms, everybody in your room, and you went and you brought them into just the even number rooms. Now your odd number rooms are empty. Okay? And so what this shows is the natural numbers is the same size as the even numbers. Okay, they're equinumbers. Okay. Great. Okay. Now, definition. A set S is countably infinite if it is equinumerous or isomorphic with the set P. Positive numbers. Okay? Okay? So if it's the same size as P, then they're countably infinite. Now, this is a little bit of an oxymoron, countably infinite, because you can't finish counting it, but you can start counting it. You can say what the first element is, you can say what the second element is, you can say what the third element is, you can say what the fourth element is also. Okay, now there's a little bit of difference between notation in my book and in Ross and Wright, because in my book I do it with the natural numbers. The same definition, but with the natural numbers. Okay? But it doesn't make a difference, because as we saw, if you're the same size as the natural numbers, you're the same size as the positive numbers. If you're the same size as the positive numbers, you're the same size as the natural numbers. So we're not going to make a difference between that. I'm going to use the notation of Ross and Wright, but I'm assuming you read this and it's pretty easy. Okay, great. So let's give some examples of countably infinite sets. Okay, the natural numbers is countably infinite. The positive numbers is countably infinite. Any others? Okay, we just saw that the even numbers is countably infinite. Okay, and we're going to see a lot more. Okay, so all these sets are countably infinite. Great. Okay. Just have to say, this goes back about 500 years ago to Galileo. And Galileo was the first person to realize that the even numbers are the same as the positive numbers. He was writing in the 1500s, and he was just shocked by this, that we use this equinumerous, we use this idea which makes total sense. When you could talk about the set of students in the class and the set of occupied chairs in the class, it makes total sense to talk about they are the same size. For every student, there's an occupied chair. For every occupied chair, there's a student. Okay? Notice it doesn't work for chairs and students, because there's empty chairs in this room. Okay? And the empty chair shows you that what? That the set of chairs is larger than the set of students. Okay, so we're going to see that. Okay, let me just go through some other examples. There's a set called square, okay, and it has square numbers. give you an example of a square number. 0 is a square number, 1 is a square number, 4 is a square number, 4 is 2 times 2, 9 is a square number, 16 is a square number, 25 is a square number, 36 is a square number, dot, 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 dot. It's a lot of square numbers. Okay? And I'm going to show you that the natural numbers, or the positive numbers, I'm going to talk about the natural numbers here, but it's the same thing. I mean, it's not the same thing, but we can figure it out. Okay. That the natural numbers and the square numbers are the same size. Now, this goes to this, 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 and of course, n goes to n squared. That goes to that. Okay? Okay. That's a scheme that shows you that these two sets are the same size. So, and I could have done the same thing for the positive numbers. Okay? And so we're going to write it over here. SQ, the square numbers, are the same as the positive numbers. Again, this is really shocking because this set is a proper subset of this set. Let's just do that. SQ, the square numbers, is a proper subset of the natural numbers. They are not equal. Okay? Just like the even numbers is a proper subset of the positive numbers. They are not equal. It's a smaller subset. There are less elements. And yet, it works. Okay? And yet, they're the same size. Okay? Let's do another set. Okay? Here, this we'll do with the positive numbers. Positive numbers are 1, 2, 3, 4, dot, dot, dot. Okay? The prime numbers, PR for prime, let's see. Okay? What's a prime number? Any number that doesn't multiply by itself. So 2 is a prime number, 3 is a prime number, 4 is not, 5 is a prime number, 6 is not, 7 is a prime number, 8 is not, 9 is not, 10 is not, 11 is a prime number. Okay? There are infinite number of prime numbers. There are infinite number of prime numbers, but as you can see, they get fewer and fewer. Okay? As you get to bigger numbers, there are less prime numbers because a lot more things can divide into it. So it's harder to find. But nevertheless, you can make a function, and you say n goes to the nth prime number. Now, it is a theorem that's 2,500 years old that says the number of prime numbers is infinite. Okay? But how infinite? Same size as this. Okay, great. So prime numbers are also equinumerous. Any questions? Any unhappiness? Good? Great. Okay, so all three of these sets are seemingly smaller than the positive numbers. They are seemingly smaller because they have fewer elements. Okay, they're proper subsets, and yet they're the same size. Question, is there anything bigger than the positive numbers? So one thing we saw already, the natural numbers has one more element, it has the 0, and yet it's the same size. Great. Great. What other sets are bigger than the positive numbers? Okay. So another set that's bigger is as follows. Again, the natural numbers and the positive numbers are going to do the same way. So let's talk about the natural numbers. So this is 0, 1, 2, 3, 4, dot, 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 dot. And a little bit more. 5, 6, 7, 8, dot, dot, dot. Okay. Well, how about Z? What's Z? Z is positive and negative numbers, whole numbers. Okay. Let's dot, 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 -4, -3, -2, -1, 0, 1, 2, 3, 4, dot, 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 dot. Okay. Okay. Now, it very much looks like that this set is the same size as this set. Okay? And so, since we're in Z, we're including negative numbers also, then Z must be much larger than this set. Okay, that's what it looks like. Okay, so if I was to do this, don't do this to your notes, hold on, don't do this to your notes, but if I was to match it up and say, okay, 0 with 0, 1 with 1, 2 with 2, 3 with 3, etc., then I wouldn't have such a correspondence. This set would be larger than that set. Okay? So that's a stupid way of trying to match them up. But there's a better way of trying to match them up, and I'd like to show it to you. I'm going to show you this proof 3 different ways. So here's the better way of doing it. Now you can take notes. I'm going to send 0 to 0. 1 to 1. 2, I'm going to send to -2. -1. 3, I'm going to send to 2. 4, I'm going to send to -2. 5, I'm going to send to 3. 6, I'm going to send to -3. 7, I'm going to send to 4. 8, I'm going to send to -4. Dot, dot, this goes on, and this goes on. Now, every one of the natural numbers is hitting both positive numbers and negative numbers. Okay? They're hitting both positive numbers and negative numbers. Conclusion, this is going to be a one-to-one correspondence between this set and this set. Okay? Now, I'm going to show you this proof 2 other ways, and 3 other ways actually, but let's just get the sum total, the answer. The final answer is this positive numbers, which is the same as natural numbers, is the same as Z. It's the same size as Z. So again, the natural numbers are seemingly bigger, Z is seemingly bigger, but no, they're the same size. And keep in mind, the positive numbers is a proper subset of the Z. The positive numbers is a proper subset of that, and yet they're the same size. That's not usual. Okay? I want to show you another way of thinking about this. Okay? Another way is as follows. Here's the natural numbers. Okay? The natural numbers goes on for infinity. It goes on one way. 0, 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. Dot, dot, dot. Okay? As opposed to that, the Z also has that 1, 2, 3, 4, 5, 6, but it also has negative numbers. -1, -2, -3, -4, -5, dot, dot, dot. -6, dot, dot, dot. Okay, great. So, both ways. Okay. So, the way to think of this is the natural numbers. Boom, 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 boom. This is Z. Boom, boom, boom. Okay? And this goes on infinite 2 different ways, and this goes infinite 1 different way. Now, I'm going to match them up the same way I matched them up here, but here you can see it a little bit more clearly with this picture. Ready? 0 is going to match up with 0. 1 is going to match up with 1. 2 is going to match up with -1. Oops, what am I doing here? This 2 is going to match up with 3. 3 in the natural numbers is going to match up with 2. 4 is going to match up with the negative. 5 is going to match up with 3. 6 is going to match up with negative. 7 is going to match up with 4. 8 is going to match up with that. Dot, dot, dot. Okay? So let's see what we did here. what we did was we took the natural numbers here and we split them into two lists. We split them into two lists, into two parts. The odd ones, 1, 3, 5, 7, are going to correspond to the positive z's. And the even ones are going to correspond to the negative z's. So again, the odd numbers are infinite. The even numbers are infinite. And so positive numbers, infinite. Negative numbers, infinite. So we were able to match them up. Okay? Very nice. We need a function for this. I can't just say I'm matching it up. I need a function. So the function is going to go like this. Okay? And I just want to say, there's a similar function given in my book. There's a similar function given in their book. They're almost the same, but you'll have to figure out they're like this. But let's see if we can do this function. So let's do it. F of n. Oh, let's just try it. Where's F going from? F is going, let's do it from the natural numbers to z. Okay? So I'm going from n to z. So we have as follows. F of n is equal to one of two things. Okay? If f is, if n is even, if n is odd. Okay. So, what did we say? If n is even, where should it go? So if it's 2 should go to -1. 4 should go to -2. 6 should go to -3. So if n is even, then take n, it's even. So it's multiple by 2, so you can divide by 2. And go to the negative of that. Okay. In contrast, if n is odd, so let's do 3. 3 is going to go to 2. So 3 plus 1 is the right. 5 plus 1 is 5 plus 1 is 6. Right? So here's what to do. If n is odd, then n plus 1 is even. Okay? If n is odd, then n plus 1 is even. Divide by 2, and that's what you get. That function does exactly what this does. Let's do it another way. Let's do another function. G goes from z to n. How about that function? If this is an isomorphism, if there's an isomorphism, that means there's a function this way and a function this way, and they're the same thing. So let's do this. How does this go? G of n is going to equal to one of two things. How do we do this? How do we do this? Let's see. 1. This goes to 3. This goes to 7. Okay, so how do we do this? This is if n is more than 0, then how do we do it? 2 goes to 3. 4 goes to, so it goes to 2 times n minus 1. Let's just see if that works. If n is 5, 5 is more than 0, it's going to go to 2 times 5 is 2 times 5 is 2 times 5 is 10. It's going to go to 9. So that works. Okay. If n is less than or equal to 0, by the way, does it work for 0? 2 times 0 is 0 minus 1. No, it doesn't. So here we do it like this. Okay, let's do this. So let's see. If it's minus 2, it should go to 4. If it's minus 3, it should go to 6. So it goes to minus. So let's just do this. If it's minus 2, it should go to 4. So it goes to minus 2 times n. Let's just plug in some numbers. Minus 2 times minus 2 is positive 4. So it goes to 4. Minus 3 times minus 2 is positive 6. It goes to 6. Okay? 0 goes to 0. Minus 0 is 0. That's a nice way of saying it. Okay? So these two functions, from n to z is f, from z to n is g, and you go back and forth. Sounds good? I want to do it another way. Okay? I want to do it another way. Okay? I'm not doing it for my own benefit. I'm doing it because we're going to see this idea over and over. So let's erase this. Okay? Now I'm going to write Z like your teacher did the first day of 9th grade. Okay, here's 0, here's 1, here's -1. Here's 2, here's 3, here's 4, here's 5, here's 6, here's 7. Here's -2, here's -3, -4, -5, -6, -7. Okay, so this is Z. Okay. And now, what I want to do, I'm just redrawing this picture, but in a more interesting way, which is very similar to what we're going to have now. Now, what I want to do is, I want to think of the natural numbers as an infinite one-way snake, just like I have over here, an infinite one-way snake. Okay, so here's the natural numbers. 0, infinite one-way snake. 1, 0, 2, 3, 4, 5, 6, 7, 8, 9. Everything okay? Sorry about that. Okay. So we have this two-way infinite set. And we have this, the natural numbers, I want you to think of that as an infinite one-way snake. Okay? And what I'd like to do is show you how I can make a correspondence between this set and this set. We did it twice already, but I want to show you the notation. The notation is as follows. I'm going to take this, I'm going to redraw this infinite snake on here. And I'm going to do it as follows. I'm going to send 0 here, I'm going to send 1 here. I'm going to send minus, whoops. 2 minus 1, 2 goes to -1. So this is 0, this is 1. This is 2 goes to -1, then 3 goes here, and then 4 goes here, and then 5 goes here, and then 6 goes here, and then 7 goes here, etc., etc. Okay? I'm bouncing back and forth on Z so that every single thing is done. Another way of saying it, I take this snake and I bounce it back and forth, and every single thing will be hit. Every single guy down here will be hit. For example, what about the number 356? Okay, well, I'm just going to tell you, eventually, boom, boom, back and forth, some guy is going to come and hit this, and then it's going to go that way. So every single number here will be hit. Okay? We're going to do this with other sets over and over. Sounds good? Okay, good. Okay. Can you press pause, please? Okay, so question, is there anything larger than the positive numbers? We tried, these sets are seemingly smaller, it's the same size. These sets are seemingly larger, they're the same size. Is there anything larger? Well, let's look at the set of all fractions. Okay? Now, the set of all fractions, not only does it go infinitely one way, okay, but it goes two-dimensionally infinite. So it would seem obvious that the positive numbers are smaller than the set. Not only that, you can see the positive numbers right over here. 1, 2, 3, 4, 5, 6, 7, ... So how the hell can the positive numbers hit every single one of these when it's just the same size as that? Okay? So turns out that they are the same size. And I'd like to show you. It's the same idea as we did over here with snaking. Okay? There's a picture of this in my book on page 75 and in Ross and Wright on page 529. A similar type of picture. In my book I call it a necklace proof. Okay? Because what you're doing is you're going around as if there was a necklace. And it goes as follows. Send 0 here, send 1 here, send 2 here, send 3 here, send 4 here, send 5 here, send 6 here, send 7 here, send 8 here, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Keep on going around and around. Oops. Around and around. Keep on going around and around until you hit every single fraction. In particular, you might have a fraction over here called 537 divided by negative 624. Well, guess what? Eventually, that thing will be hit. You'll come around and you'll hit that number. So every single positive number will hit every single fraction and vice versa. So it's wrong to think of this, even though it's two-dimensionally infinite, still, because we can make such a one-to-one correspondence, because we can make such an isomorphism, because we can show their equinumerous, because we can match up every one of the positive numbers with every one of the fractions, that's why you can show that fractions are the same size. So that's a very nice thing. Great. Okay, now what I'm going to do is I'm going to ask question, is there anything larger than this? Is there anything larger? Okay, so we saw everything is, well, a larger set than this is the real numbers. This is what your teacher drew the first day of 9th grade, and it said the real numbers. Now the real numbers is not just does it have whole numbers, like this, not only does it have fractions, but it has all numbers. For example, it has pi, it has e, it has the square root of 2. These are numbers that cannot be written as fractions. So a typical number here will be 4.863266712 infinite expansion. Okay? They will go on forever, they will not repeat. Okay? Fractions repeat. These guys do not repeat. It has those guys that repeat, it has all these things, but it turns out, but there's a lot more in here. Question, are these the same size? Is this the same size? Okay. So all this idea goes back to a guy named George Cantor, who lived in the 1880s, 1890s. He was the one who, I mean, he wasn't the first, because like I said, Galileo did it, but he was before Hilbert. I mean, he's a little older than Hilbert, and he was the one who said, you know what, let's do this thing. Let's take this idea of two sets being isomorphic, and let's go for it. Okay? And he was the one that showed a lot of these different correspondences and said, look, they're the same size. Okay? And then he saw this and he said, okay, let me try to find a larger set. So he said, hey, this seems to be the larger set. And he said, maybe this is the same size as the natural numbers, the positive numbers. So he tried different schemes. He said, okay, I'm going to send 0 here, I'm going to send 1 here, I'm going to send 2 here, I'm going to send 3 here, I'm going to send 4 here, I'm going to send 5 here, I'm going to send 6 here. He was bouncing around trying to hit every single real number. And every scheme that he had, he failed. He just couldn't do it. He tried so many times, and he was thinking about it so deeply and so often, that he went crazy. Literally, he went to an insane asylum. Okay? He got out of the insane asylum, okay, and he decided, on condition that he doesn't think about these things, he decided to try something a little bit easier. You know what? He said, look, When it comes to the real numbers, I'm having a hard time getting it. When it comes to the real numbers, I'm having a hard time making the connection between the positive numbers and the real numbers. But let me try something a lot smaller than all real numbers. How about just the interval from 0 to 1? Okay? In other words, just these guys, from 0 to 1, not including the 0, not including 1. Can I show that these two sets, he wasn't able to do this. He wasn't able to show that they're the same size. He wondered, maybe he can show that these two are the same size. So he tried very hard. Okay? Let me just show you what he was trying to do. I'm going to blow this up a little bit so you can see it clearly. Okay? Here's 0, here's 1, here's 0.5, here's 0.25, here's 0.75. But there's a lot of irrational numbers there. And he said, you know what? Let me try bouncing around in here, trying to zigzag, or what did I call it? Necklace, zigzag or necklace my way through here. Okay, so he said, you know what? Maybe I'll send 0 here, and 1 here, and 2 here, and 3 here, and 4 here, and 5 here, and 6 here, and 7 here, and 8 here, and 9 here, and 10 there, He tried many different schemes, but every scheme he tried failed. Every scheme he tried failed. There was always some extra guys here. There was always some extra real numbers. Just like, think about this room, okay? I told you before, the set of students is equal to the set of occupied chairs. What about empty chairs? What about the set of all chairs? So, even if I mixed you guys around and said, you go sit here, oh, there's an empty chair, you go sit there, you go sit there, you go sit there, it's still not going to help. Why? Because there are more chairs than students. So there's no way I can match up students and chairs. There's absolutely no way I can match up students and chairs. So we have this problem. Okay? So he tried as much as he could. He tried one way, he tried a different way, he tried a different way, he couldn't do it. Again, he went to an insane asylum. Again, he got out of an insane asylum. And then he proved an amazing theorem. Okay? He got out, he stopped thinking about it for a while, but after a while he started thinking about it and he proved an amazing theorem. Much more interesting than that. What he proved is that the reason why he was having a hard time making a correspondence between this set and this set was not because he was stupid, not because he didn't have the brains to do it. The reason why he was having a hard time doing this was because no such correspondence existed. No such correspondence existed. You cannot make a correspondence between this set and this set, which means that this set really is larger. Just like the set of chairs in this room is really larger than the set of students in this room. And the reason for that is because there are more chairs than students. So too, I cannot make a correspondence between students and all chairs. So too, I cannot make a correspondence between the set of positive numbers and the set between 0 and 1. Okay? I'd like to go through it and show you the proof. Okay? It is a beautiful proof and it's very important. So the proof it's called the proof by contradiction. So let's just say this. The set 0, 1 is not the same size as that set. It's totally different. I made it in a different color. It's wrong. It's not the same size. Okay? Okay, let me show you the proof. The proof is what's called a proof by contradiction. A proof by contradiction means I want to prove to you that this set is not the same size as this. How do I prove it? I assume it is the same size, and I get a contradiction. Okay? I get a contradiction. There are no contradictions in mathematics. Conclusion, my assumption must be wrong. Okay, so let's do that. Okay, so let's try to assume that there's some type of correspondence between the positive numbers and the set 0, 1. Okay, So let's write down the positive numbers. 1, 2, 3, 4, 5, 6, 7, 8, dot, dot, dot. Okay? And I'm going to write down, I'm going to assume that there is a scheme. Okay? So the scheme looks something like this. 0.8632441238691107, and 2 is going to correspond to 0.53199621756 dot dot dot, and 3 is going to correspond to 0.75000000000000 dot dot dot. That's a rational number. 0.75 is 3/4, but it's in our set, so we have to hit every single one. Okay, and this is going to correspond to, I don't know, I'm making this up as I go along. 6, 6, 6, 6, 6, 6, 6, 6, da, 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 da. And 5 is going to correspond to 0.912341776, da, 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 da. And 6 is going to correspond to 0.1000000, da, 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 da. And 7 is going to correspond to 0.332511162, da, 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 etc., etc. This goes on forever and ever. I'm just describing a scheme. Okay? Just like I showed you the first few elements of Z, where it goes to, I'm showing you the first few elements. But assuming there is such a correspondence, what I'd like to do is, I'd like to show you a number that's not on this list. I want to show you a number that's not on this list. Okay? So let me show you that number. Ready? I'm going to call that number D. D is going to stand for diagonal. Okay? And it goes as follows. You see this 8. I'm going to choose a different number than 8. So D is going to equal to, it's a number in here between 0 and 1, so it's 0 point, I'm going to call it 2. 0.2. Hold on, I'm not finished describing this number. But one thing I can tell you already, if this is an 8 over here, 0.8, and this is 0.2, it's not this 0th number. I'm sorry, it's not the first number. It's not this number. This number is not this number on the list, because this starts 0.8, this starts 0.2. Okay, here's a 4. I'm going to choose another, there's a 3, I'm going to choose another number besides 3. I'll choose 9. Oops, so here I chose 2. Here I choose 9. Okay. Now, I can tell you one thing. This number is not this number on the list, because that starts with an 8, this has 2. It's not this number on the list, because this has a 3, and that has a 9. They're different numbers. Okay? And you see this? Notice what I'm doing here. Okay? Notice what I'm doing. This is the first position, this is the second position, this is the third position, this is the fourth position, this is the fifth position, sixth position, seventh position. Okay? I'm looking at the first number in the first position, and I'm changing that number. I'm looking at the second number in the second position, and I'm changing that number. And I'm looking at the third number in the third position, and I'm changing that number. It was a 0, I'm making it, pick a number, a 5. So it's a 5. Okay. Now, I found this number, and it's different than the first number on the list, the second number on the list, the third number on the list. I keep on doing this. I just keep on changing numbers on the diagonal. Dot, dot, dot. D for diagonal. I'm going through the diagonal, and whatever number there is here, I'm using a different number. He has a 6 here, I'm using a 7. He has a 4 here, I'm using a 0. He has a 0 here, I'm using a 2. He has a 1 here, I'm using a 3. He has a 0 here, I'm using a 1. Whatever number there is, I'm using a different number. So far my number is 0.2957023 1, dot, 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 dot. Okay? I found this number to be different than every number on the list. Now, if you claim that this is a one-to-one mapping from this set to this set, then every single number between 0 and 1 has to be on this list. So question, where the hell is this number? Where's this number? You tell me every number's on the list, where's this number? Now, you can answer, okay? Student says, you know what, this number is on the list. It's the 732th number, 732th number. Oh, it's the 732th number? Oh, I didn't know that. Let's see. That means the 732th number is 0.29570231. Hold on, let me ask you a question. What is the 732th digit of the 732th number? Okay, if you wrote, give me a number.
5.
She says 5, guess what? I chose 6, just to be different. Conclusion, don't tell me that this number is the 732th number, because this number is different at the 732th digit. Then this number is different than your number. Conclusion, it's not on this list. Okay? Great.
Can you say that again?
Yeah. Let's go through this again. You ready? You claim that every single real number between 0 and 1 is on this list. I'm saying it's not on this list. It's not the first element, it's not the first number, it's not the second number, it's not the third number. Now, I go ... here, I say this is a scheme. Okay? I can't list off all the numbers because it's an infinite number of things. So we say, oh, it's the 732th number. No, it's not the 732th number, because this number was chosen to be different than the 732th number. Because she says this number has a 5 in the 732th position. Guess what? My number has a 6 in the 732th position. They look the same, 295702231, 295702231, but they're different. Good? Okay. Now, you can't give up so easily. You can't give up so easily. You might want to make another scheme and say, hey, let's try another scheme. Right, this scheme didn't work, but let's try another scheme. Okay? The other scheme will do something like this. Don't move. The other scheme will do something like this. Let's try it again. A different scheme. 1, 2, 3, 4, 5, 6, 7, ... Okay? And we're going to look at all the digits. Okay. Now, in this other scheme, you're going to want to put in all the numbers. So let's do it. 0.53126217991 ... 2 is 0.2500000000. 3 is 0.88128123662 . 4 is whatever. Okay? Oh, you better make sure this number is in your list, because you missed out this number last time, right? So you better make sure it's in your number this time. So 0.2957023 . Okay? And this is going to go on forever and ever. This is another scheme. Your first scheme failed. Here's another scheme. And guess what I'm going to do? I'm going to find a number that's not on this list. Just like if you're trying to make a correspondence between all the students and all the chairs, you can mix them up as much as you want. I'm always going to find an empty chair. Okay? You can mix them up again, and you can mix them up again. I'm always going to find an empty chair. Why? Because the number of students is less than the number of chairs. The number of chairs is more. So too, so I'm going to find a new number. The new number, we'll call it D. Okay? You have a 5 here. I'm going to choose 0.6. You have a 5 here. I'm going to choose an 8. You have a 1 here. I'm going to choose a 9. You have a 7 here. I'm going to choose 3. Okay? This new number, D prime, is going to be different than every single number on your chart. Okay? conclusion, it doesn't work. There is no scheme, there is no function matching up the positive numbers and the signs of 0 and 1. Doesn't exist. No such function exists. Okay? There are literally more guys. There are literally more of these guys than there are of these guys. Okay. You want to stop? You gotta go. Okay, so let me just say, do you have to go?
No.
Okay, so let me just say, I'm going to go on for another little bit because I can, and I'm going to put this up on the internet tonight, whatever. But I just want to say the answers to the homework questions from chapter 13, 13.1, 13.2, and 13.3 are in this booklet. Okay, so again, I strongly urge you to read this chapter, then go look at this book, and then the answers to the homework questions are at the end of this chapter. They're right here. So you have the answers, and we'll go through. Sounds good? Okay, good. Thanks a lot for your help. Okay, I want to go on. There's another set that's not. That's we need a definition. Okay, so where we have a new thing, we have two different levels of infinity. We have countable infinite and uncountable, and countable infinite and those things that are not. Okay, so not everything is the same size as the natural numbers. Okay. So now we make a new definition. By the way, I'm gonna try to do this next Tuesday also. Okay. You're welcome to come. If you don't come, that's fine also. But I think I'm going to do two classes so that I can get up ahead of schedule. Okay. If you come, great. Okay. Definition: set S is uncountably infinite. If there is no one-to-one I said S is uncountably infinite if there is no one-to-one correspondence between S and P. Okay? And the idea is, again, uncountably infinite, all infinite sets can't be counted. But here you can't even begin to count them. Why can't you even begin to count them? Because you can't start. Where do you start? What's the first number? What's the second number? What's the third number? You can't say. Countably infinite, there exists a way of doing it. So there is no. Here, uncountably is larger. Okay? Okay, great. So, I want to go through just to say over a few things, and then we're going to finish section 13.3. Okay? And again, you're going to have to read it both in my book and in this book. One of the questions, is there anything else larger than that? Than the positive numbers? And the answer is yes. The real numbers is also larger than the positive numbers. Okay? Now we saw that this is a subset. This is one part of it, this is the whole thing. Okay? Question. We just showed that this is uncountably infinite, 0, 1. What about this? You would think it's even more, because just look at what it is. Oh, sorry, I'm going to erase this. Now, again, this is the real numbers, we just showed that just this set itself from 0 to 1 is uncountably infinite. How about the whole thing? Okay? And the answer is, you might say, oh, the whole thing, this goes infinite. Notice this arrow is infinite. That's pointing towards, that's Bedford Avenue, that's pointing towards Manhattan. That's pointing towards Sheepshead Bay. That's talking to the Atlantic Ocean. That goes on forever. Okay? So, how could it be this set is uncountably infinite? What the hell is that whole set? Okay? And the answer is something I talk about in my book. It's called, I call it the sunshine theorem. Okay, the more exact words is the stereographic projection or something like that. I want to take this set and I want to pick it up and fold it over. So it's going to be like this. Just the set 0 to 1. Okay? I pick this set up and I fold it over. Okay? And I want to call this set the sunshine theorem. I want you to think of that red dot as the sun, and I want to show you what this is. Before we do this, I want to show you. If this is 0 and this is 1, then let's say this is 0.5, this is 0.25, this is 0.75. Okay, we have all these different numbers. Okay. Well, now I want to show you that the set 0, 1, although it's a proper subset of the set of all real numbers, still they're equinumerous. When do you want me to leave?
Because we booked this room for our meeting, so it's something.
What time?
12:30, but, okay.
Okay, so I'll be there at 12:35. Okay, so this set is the same size as this, and the theorem is as follows. It goes as follows. I'm going to match up every one of these with every one of these. This guy is going to match up with this guy. This guy is going to match up with this guy. This guy is going to match up with this guy. I just drew a straight line from the sun through 0, 1 till where it hits. And this guy is going to match up with this guy. Now you might say, hey, but that's silly because this set is a lot bigger than this set. Doesn't matter because you can split every element, split every point like that. Okay? And now take some number on the real line over here, it's going to match up something like that. And take some number over here, it's going to match up something over here. Okay? So every one of these guys matches up to every one of these guys, every one of these guys matches up to every one of these guys. Conclusion, these two sets are the same size. Conclusion, they're both uncountably infinite. Okay? Now, another thing. Okay? And you're going to read this in my book, and you're going to read this in the book here. It's as follows. Let me show you some other uncountably infinite sets. Take the positive numbers. 1, 2, 3, 4, 5, 6, 7, 8. Take the power set of the positive numbers. That's subsets, all the subsets of the natural numbers. Okay? Turns out, and the book goes through a nice theorem, my book, both books go through a nice theorem, that there's no way in the world these two sets are the same size. Power set is always bigger. It contains everything, including, it always has more elements than this. Now we saw this in class when we talked about a finite set. We said as follows. If you have a set that has n elements, then the power set of S has 2 to the n elements. We saw that in class. Okay? So with finite sets, if you have a finite number here, then 2 to the n is bigger than n. So that's always true. Okay? But here, we're saying even for infinite sets, if you have an infinite set, this is bigger. Which means this set is not the same size as this. What do we call sets that are not the same size as the positive numbers? They are uncountably infinite. So the power set of P is uncountably bigger. Okay? Now, it turns out this is true not only for S, okay, not only for P, for any set whatsoever. Take any set whatsoever, okay? The power set of S is not the same size. The power set of S is larger than S. Okay? So they're bigger. Great. Okay. Now let's go through some more examples. Let's put all our examples up on the board. Okay, we saw that this set is not the same size. So we have a new set. We call it 0, 1. The real numbers, the power set of P. Okay. All these sets turns out to be the same size as each other, but not the same size as this. Okay. It turns out any of these sets, you can choose any of these sets. For example, the power set of Q. Well, Q is in here, the power set's going to be bigger, and these sets are going to be the same size. But then you could do something really radical. You can not just look at from these countably infinites, look at any of these. How about this? The power set of 0, 1. It's amazing. So 0, 1 we said is not the same size as this, it's bigger. So we know here, that's even bigger than this. They're not the same size. Okay? When we talk about the power set of the real numbers, those two are the same. And the power set of the positive numbers, those two, they're all the same, etc., etc. But what we showed was, for any set S, the power set is bigger than S. So we can go on building more and more sets. So not there's 2 levels of infinity, there's many levels of infinity. In fact, there's an infinite level of infinity. Okay? Many, many different levels of infinity, and none of them are, one is bigger than the other. None of them is the biggest one. It just goes on and on. So this is an amazing thing. Now, I just want to talk about how this is done. In one of the books, I showed this in my book, but in the other book it shows us as follows. Instead of talking about the power set of P, what it talks about is functions from P to the set 2. Remember the set 2? We talked about that when we talked about characteristic functions. Okay, that's the set 0, 1. So if you want to talk about the power set, so this is the same size as the power set of P. Okay? What's a power set of P? It's a set of all subsets. How do you describe a subset? It's a characteristic function, a function from the power set to the 2. Remember this? Psi A is a subset. It goes from the power set to the set 0, 1. From the positive element to just the 0, 1. So if you look at, which is another way of saying 2. So if you look at all sets from here to there, you get that. Okay? So some of the stuff at the end is a little bit more harder, but it's fine. I'm just showing you another thing. One of the homeworks is to ask you to prove that the set of functions from the positive numbers to the positive numbers is uncountably infinite. So and the answer is, well, if this set is uncountably infinite, this set is definitely uncountably infinite. Great. Just a little notation goes as follows. I know what to call a set that has 3 elements. I call it 3. I know what to call a set that has 4 elements. The size of that set we call 4. I know what to call a set that has 5 elements. I use that symbol, etc., etc. Okay, what do I call all these sets that have this size elements? Okay, and Cantor gave an answer. He said, call it Aleph 0. Aleph 0 is Aleph is a Hebrew letter. He says Aleph 0 is the beginning of infinity in some sense. Okay? Cantor wasn't Jewish, but he knew the Hebrew alphabet, so he did that. Great. What should I call these sets that have these sizes? Well, just look at this main example. If you have here the positive numbers and here the power set of the positive numbers, okay, then just to remind you, we just had a theorem I just had here. If S has n elements, then the power set of S has 2 to the n elements. So if P positive numbers have Aleph 0 elements, then the power set of the positive numbers should have 2 to the Aleph 0 set. Okay? So that's the notation that we call sets that have this size. And guess what we're going to call this? If this has Aleph 0, then this has 2 to the Aleph 0, and this has 2 to the 2 to the Aleph 0. So this set has size 2 to the 2 to the Aleph 0. And you can go on with this. Okay? Now, in the book, one last thing and we'll let you go. In the booklet, in my book, which I gave you the free chapter here, we asked the following question. Okay? I didn't ask the question. Cantor asked the questions in the 1890s. Okay? Question, is there anything in between here? Is there any infinite number in between here? Okay? So if I ask you, is there any number between 3 and 4, you'll tell me no, if you're talking about natural numbers. But if you're talking about real numbers, yeah, how about 3.5? That's in there. Okay? So I'm asking you the same question. You have an infinite amount. You have another infinite amount. Is there something in between there? Little side story. Okay? Cantor believed that the answer was no. He called that, this is in section 4 of the book, you're not really responsible, this is just a little bit outside. He said, nothing in between. He said he felt it was true, he didn't prove it. He said nothing in between, and that idea is called the Continuum Hypothesis. There's nothing in between. Okay? And Cantor felt that this was true, but he couldn't prove it. In the 1930s, Kurt Gödel, one of the great mathematicians, he proved that if you answer no, that there's nothing in between, you won't get into any trouble. You won't get any contradictions. He's not saying that the answer is yes, but he's just saying if you answer no, that there's nothing in between Aleph 0 and 2 to the Aleph 0, you won't get into any contradictions. Okay? And then in the 1960s, so this is Gödel. I'm reading this all in my book. In the 1960s, a man named Paul Kohn proved the following theorem. He said, if you answer yes, there is something in between here, you won't get into a contradiction with your logic. You won't get into a contradiction. Okay? So he said the answer could be no, and he said the answer could be yes. Either way, you won't get into a contradiction, which means that we don't really have the right answer to this question. We don't have the right axioms to this question. Just one small point. Paul Kohn went to Brooklyn College. Okay, he spent the first 2 years of his undergraduate in Brooklyn College. He never graduated. He's a dropout from Brooklyn College, but he went to the University of Chicago and he got a PhD. And he won, for this work, he won the highest award in mathematics, called the Fields Medal. But again, he went to Brooklyn College. That's where he got it. So Brooklyn College. Okay, thank you very much. Again, the answers to the homework questions in chapter 13 are in the booklet. I will gladly go through anything if you have an email question or something like that. And next time we start chapter 3, which talks about relations. Take care. Stay safe.